Good morning. Let's finish chapter 6 with this last part of the recording. We finished facilitated diffusion and filtration. Now we are talking about active transport. As you know, by definition, active transport is moving molecules against concentration from low concentration to high concentration. I drew this picture for you. If you want to move this ball up against the concentration, you have to spend energy. So we are saying active transport moves molecules uphill. To do so, we need to spend energy. And the structure that moves these molecules against the concentration is called pump. Pump is a protein that can grab a molecule and using force move it against the concentration. Pump is a carrier-mediated protein, and they show the same characteristic that you saw for the protein in the case of facilitated diffusion. Remember, in the case of facilitated diffusion, we had stereospecificity, we had saturation, we had competition. Here, that one also applies. Every time you use a carrier-mediated protein, the same characteristics that we discussed before applies there as well. So there are three different types of active transport. The first one is called primary active transport. What is primary active transport? Let's take a look at this example. Here is inside the cell, here's outside the cell. You know, majority of calcium is outside the cell. Inside the cell, we have low calcium. Calcium likes to get in from higher concentration to lower concentration. If calcium managed to come inside the cell, then this protein, which is called pump, which is a carrier-mediated protein, is going to grab this calcium and says, hey, I told you have to stay outside. And it's going to push the calcium out. To move it from low concentration to higher concentration, uphill, we have to spend energy. This pump is going to break down ATP, and as a result, create ADP and pyrophosphate, or PI, and move this calcium out. Because this pump directly breaking down ATP is called a primary pump. So by definition, a primary pump is a pump that uses ATP directly. Here's another example of primary pump, which is the most important pump in our body. Every cell in our body is going to have this pump. Now, I'm sure you know that if this is a cell, inside the cell we have lots of potassium. Outside the cell we have lots of sodium. If you change this composition, the cell cannot survive. Sodium wants to get inside the cell. Potassium wants to get outside the cell. But if that happens, my cell is going to die. It's going to become dysfunctional. I have to keep potassium inside the cell. I have to keep sodium outside the cell. If this sodium managed to come in, or if potassium managed to get out, there is a pump here, and this pump is going to force this sodium and potassium to go back where they were. It's going to grab potassium and bring it back in, and it's going to push sodium out. So let's take a look at this pump. We're going to start from here. As you can see, here's inside the cell, ICF. Here's outside the cell, ECF. And this is a protein that moves sodium and potassium. Let's just start from the time that this pump is facing inside. When the sodium sneaks inside the cell, this pump is going to grab 3 of this sodium. This 3 sodium is going to sit here. You may ask why sodium is going to come and sit here. Well, it happens that this pump in this protein has 3 seats with a very high affinity for sodium. You don't need to know what creates this high affinity for this class, but just accept the fact that these seats, they have a high affinity for sodium. As soon as sodium is going to sit here, this pump is going to break down ATP and turn it to ADP and phosphate. Phosphate is going to attach to the pump. Remember, this pump is protein, and we already talked about 3-dimensional shape of protein. The 3-dimensional shape of protein is extremely important. If anything attached to a protein can change that 3-dimensional shape. As a result, every time phosphate attached to a protein, or phosphate is going to detach from protein, the shape of the protein is going to change. In this case, as soon as phosphate is going to attach to this protein, the shape of protein is going to change. As you can see, the protein is going to get closed. There is no opening for this protein anymore. Later, this pump is going to release ADP. Remember, we break down ATP to ADP plus P. As soon as this pump releases ADP, again, something is releasing from the pump. the shape of the pump is going to change, and now pump is going to open to the outside. As soon as this pump opens to the outside, the affinity of those seats for sodium is gone. Now we are dealing with different shape. Now the pump has no affinity for sodium. Tell the sodium, hey, get out, I don't like you anymore. Sodium, because has no attraction toward these seats, is going to get out. But potassium has a high affinity for pump now. As soon as potassium is going to sit here, this pump is going to release phosphate. And again, as you release phosphate, the shape of this protein is going to change. And you remember when you release phosphate, the pump was open toward inside. And that's exactly what's going to happen. This pyrophosphate, or PI, is going to get released. The shape of the protein change, opens to inside. Again, it's going to lose the affinity for potassium. Potassium is going to get dislodged. Now, the shape of the pump is the way that has a very high affinity for sodium. Make a long story short, the first thing you have to understand is this pump moves 3 sodiums out and bring 2 potassium in. So 3 sodium versus 2 potassium. And 2, the reason that the shape of this pump is going to change is because of attachment or detachment of ADP or phosphate. 3-dimensional shape of protein is extremely important for the function of the protein. This is a summary of what we just said. This pump is going to bring potassium in, 2 of them. It's going to take out 3 sodium. Here's another example for primary pump. It's called proton pump. You remember the ion for hydrogen is called proton. I know this picture is kind of complicated. We're going to get to that later. So don't worry about those details. Just follow me through. This is a cell for stomach. Here's inside the stomach. It's called the lumen of a stomach. Here's outside the stomach. Is interstitium. As you know, inside the stomach, we have a high amount of proton or acid. This cell is supposed to pump acid inside the lumen or inside the stomach. How does this one work? Well, it's very simple. Because inside the cell we have high potassium. Why do we have high potassium inside the cell? Because of sodium-potassium pump. Sodium-potassium pump is going to increase potassium inside the cell, as we mentioned. So inside of every cell, regardless of what cell, we have a lot of potassium. Therefore, we have a lot of potassium here. This potassium likes to get out from high concentration to low concentration. There's a channel here that potassium is going to get out. It's going to get inside the lumen. But there's a pump here, and this pump is going to tell potassium, hey, I told you that you cannot get out. So this pump, in this case, is going to bring potassium in, but it's going to take hydrogen out. Because of this pump, you're bringing potassium in. Potassium is going to get out through this channel, so potassium is going to go through this cycle, but every time this happens, you're putting one more hydrogen out. This pump is going to do so by spending energy, by spending ATP. Therefore, we call this pump a primary pump. So every time a pump uses ATP directly, it's called a primary pump. That's a second example. So now, let's move on to secondary active transport. What's secondary active transport? A secondary active transport is an active transport that the function of that protein depends on the primary active transport. Let's take a look at this one. This is my primary pump. It's a proton pump. It's not the same as the one you saw a few minutes ago in the stomach. This one is not in the stomach. This is in your small intestine. What's the function of proton pump? It's a pump that pushes proton against the concentration. Majority of the proton is outside the cell. Inside the cell, we have less proton. Proton wants to get back inside the cell. But as soon as proton comes inside the cell, this pump is going to grab proton and says, hey, you need to stay out. It's a primary pump because it's using ATP directly. So we know this pump already is a primary pump and push the proton against the concentration uphill where you have more proton. Now, we have another protein here. This protein is called secondary pump because it depends on this pump. How? Remember, proton is more in the outside the cell, right here in this area. Proton cannot go through the cell membrane because proton is an ion and cell membrane doesn't allow ion to go through. So proton is going to come to this protein and says, hey buddy, can you let me in? This protein is going to tell the proton, yes, you can come in, but I'm going to bring a sucrose, which is a sugar, with you inside the cell also. Obviously, proton is going to say, I don't care. So therefore, proton and sucrose together, they're going to get inside the cell. Sucrose by itself cannot come inside the cell. proton by itself cannot come inside the cell, but this pump can move them together inside the cell. This is the cells of a small intestine. When you eat food and your blood sugar goes up, this is the way to bring sucrose inside the cell. Now, here's the idea. If this proton pump doesn't function, what do you think is going to happen? Well, we have lots of proton here. So this proton and sucrose, they're going to come inside the cell, but proton is not going to get out because this pump is broken. So as a result, at one point, we have lots of proton that this proton from outside doesn't want to get in. When the proton doesn't want to come in, then the sucrose cannot come in either. In other words, this pump becomes useless. Let's repeat one more time. We have a lot of proton here. This proton is going to come to this pump and try to come in, and of course this pump is going to bring sucrose in at the same time. This proton is going to come inside the cell and is supposed to be pumped out. If this pump doesn't work, if this primary pump doesn't work, so proton keep coming in, but they're not getting out. As a result, at one point, you have lots of proton inside the cell. Therefore, no more proton wants to come in. If proton doesn't come in, then sucrose cannot come in. That means this pump becomes useless. Therefore, we call this one a secondary pump because this pump depends on this pump. If this pump doesn't work, this one also is going to stop working very shortly. Here's another example for secondary active transport. Again, this one happens in the wall of a small intestine. Remember, we have a primary pump, and that is sodium-potassium pump. Remember, we have a lot of sodium outside the cell. Sodium wants to come inside the cell, from higher concentration to lower concentration. But sodium is going to have a hard time to pass through the cell membrane because cell membrane is phospholipid and sodium is water soluble. Therefore, sodium is going to come to this protein and tell this protein, hey, can you let me in? This protein is going to say, okay, you can come in with glucose. So sodium and glucose together, they're going to get inside the cell. As soon as sodium comes inside the cell, this pump is going to pump the sodium out. So sodium keep going through this cycle, and as a result, every time sodium comes in, one glucose comes in also. Imagine if this pump is not working, if the sodium-potassium pump is broken. Then, if you have 1,000 sodium outside, as soon as 500 this sodium comes in, then the sodium doesn't want to come in because now you have equilibrium. Sodium doesn't want to come in, that means glucose cannot come in, that means this pump becomes useless. Again, the function of this pump depends on the function of sodium-potassium pump here. Therefore, we call this one a secondary pump because it doesn't break down ATP directly, but depends on this pump that breaks down ATP itself. Now, we have two different types of secondary active transport. Look at this picture. Technically the same picture you saw a few minutes ago. This is the lumen of a small intestine. You're trying to bring sugar inside the cell. Remember, glucose is going to come inside the cell with sodium together. Since this pump moving both of them in the same direction, we call this one a co-transport, or it's called symport, because both of them they're coming in. Look at this example. In this example, this is secondary pump also. Bring sodium in, but take calcium out. That means they're moving in opposite direction. When this secondary pump moves molecule in opposite direction, we call this one counter transport, or it's called antiport, or it's called exchange. I'm sure by now you understand how it works. Here's a cell, here's a sodium-potassium pump. Remember, sodium-potassium pump is going to pump sodium out and bring potassium in. So, sodium is outside the cell. Sodium wants to get inside the cell. It's going to come to this protein and says, hey, can you let me in? This protein says, yes, you can come in, but I have to take calcium out. Sodium says, I don't care. Go ahead. So therefore, every time sodium comes in, one calcium is going to get out. Sodium comes in, this pump is going to grab sodium and send it out. As you can see, this pump is going to move two ions, but in opposite direction. Therefore, we call this one counter transport, antiport, or exchange pump. And the last part of this discussion is about moving a bulk or big size molecule. If you are dealing with a big size of molecule, a large molecule that cannot pass through this type of protein, then how are you going to bring them in, or how are you going to send it out? In this case, we have to use what is called a vesicular transport or bulk transport. In this course, we're going to talk about movement of proteins or hormones or neurotransmitters These are not small, tiny ions that can pass through the channel. We have to be able to move a larger molecule in and out of the cell. This process also needs ATP. Therefore, we call it active transport. Let's take a look at this example. Let's say you want to bring this large molecule inside. If you want to bring a large molecule inside, as you can see, your cell membrane is going to invaginate, create a vesicle, and now you have this content inside the cell. With the same token, if you want to move a large particle out, let's say this cell made big proteins, let's say this cell made hormones, and you need to send it out, then this protein is going to be inside the vesicle. The vesicle is going to come and fuse to the cell membrane, become part of the cell membrane. Now this product is out. That is called exocytosis. The previous one is called endocytosis. Endo, inside, exo, outside. If you bring inside, it's called endocytosis. If you send outside, it's called exocytosis. I like to start with endocytosis. As we said, means bring material inside the cell, and has two forms. One is called phagocytosis. Phagocytosis, if you try to bring a chunk of material inside the cell. For instance, if you want to bring a bacteria inside the cell, if you want to bring a germ inside the cell, your cell is going to extend itself. It's called pseudopod. It's going to extend some false leg and surround this particle or chunk of material that you want to bring in. This type of cell that is able to do such a thing is called phagocyte. And this process is called phagocytosis. So phagocyte is a cell that can extend itself and grab a chunk of material and bring it inside the cell. That chunk of material can be a solid food, or can be a bacteria, or it can be even another cell. Do you remember? Phagocytes are the cells that are able not only take the germ in and destroy the germ, but also if another cell is not functioning well, if that cell is, let's say, tumorous, if the cell is not functioning correctly, this phagocyte can go ahead and grab that dysfunctional cell and destroy it. By definition, phagocytosis is a form of endocytosis. You bring a chunk of material in while the cell, which is called phagocyte, is going to extend itself and creating pseudopod. Now, as a side note, do you know how this phagocyte knows that another cell is damaged and needs to be taken away? Well, the answer is this is a cell, and this is supposed to be cell membrane. Remember, cell membrane has two layers of phospholipid. Do you remember that? So we have inner membrane and we have outer membrane. These two are both phospholipid. The type of phospholipid that you have in the outer layer is different than the one that you have in the inner layer. One type of phospholipid that you have in the inner layer is called phosphatidylserine. Phosphatidylserine is a phospholipid and is found inside the inner membrane. If phosphatidylserine is going to come to the outer layer, that is going to signal that this is a bad cell. So how does my phagocyte knows I'm dealing with bad cell? This phosphatidylserine from inside the cell is going to move to the outside layer, and as a result, my phagocyte knows that this is a bad cell and is going to come and get it. Isn't it interesting? So that is your phagocytosis. Let's talk about another type of endocytosis. This time, instead of bringing a chunk of material, we're going to bring something that is dissolved in the fluid outside the cell. So that's why we call this one cell drinking or pinocytosis. We bring things in which is dissolved. It's not a chunk of material, but is dissolved in the fluid outside the cell. Here is one form of pinocytosis. Here's outside the cell, here's inside the cell. How this one works? Well, we have different forms, but this is one form of pinocytosis. Here's my cell membrane. This is cell membrane. In one part of cell membrane, there are some protein that is accumulated here, and that is called clathrin. At the same time, we have some receptor here in the same area. Therefore, we call this area clathrin-coded area. This receptor is for a specific structure, a specific ligand. So let's say this specific ligand is hepatitis C. Let's say is a virus, is a specific virus. or let's say this one is cholesterol. It can be anything. As soon as this virus is going to come and sit on this receptor, that is going to signal this clathrin, and clathrin is going to pull this membrane in, and it's going to create invagination. It's going to create a deeper pit. So the function of clathrin is pulling this one down. As soon as this one starts moving down, more clathrin is going to come to help, and finally they're going to pull it in and in further until it becomes a vesicle. As a result, this vesicle bring in this virus or this cholesterol, whatever it is, this ligand. As soon as the vesicle is inside, this clathrin is going to leave this vesicle and it's going to go back again and sit where it's supposed to sit. Now we have vesicle with a receptor. Inside the vesicle we have this ligand. Endosome quickly comes and attaches to this vesicle, and as a result, as soon as endosome attaches to the vesicle, this receptor is going to let this ligand go. So ligand is going to come inside the endosome. The vesicle and the receptor now is going to get recycled back to the surface area, and they're going to move to where the clathrin is. Now this endosome with this ligand inside can go to different destinations. You can attach this one to the lysosome to destroy it, or you can recycle it. So the point of the discussion here is this. In this type of pinocytosis, you bring material in, you bring molecule in when they sit on the receptor. Therefore, this type of pinocytosis is called receptor-mediated pinocytosis. It happens because of the receptor. This is a very specific type of pinocytosis. Now let me give you an example. Why is that? The virus, which is called hepatitis B or hepatitis C, they can affect your liver, but they cannot affect your neuron. How come they cannot affect your bone or muscle, but they injure your liver cell? Because a liver cell has receptor for that receptor. If that's hepatitis C, it's going to come and sit on the receptor, and as a result, it's going to come inside the cell and damage your liver cell. But because we don't have this receptor on the muscle cell, hepatitis C virus cannot damage your muscle cell, or they cannot damage your neuron, but can damage your liver cell. Let me give another example. As you know, some people, they have genetically high cholesterol. For some reason, their cholesterol is going to go up dramatically, although they are not consuming that much of cholesterol. What is the problem? Well, the problem is that these people, they don't have receptor for cholesterol. As a result, cholesterol cannot come in to be metabolized. Cholesterol is going to stay inside the blood, and it's going to cause damage to the blood vessel. So the point here is this. These receptors would be so important for this process. If these receptors are damaged or are not working, then bringing those specific proteins or material inside the cell will be impeded. We have another type of pinocytosis that is not receptor mediated. In other words, still you can bring the material in without even using this receptor. But yet, still we have clathrin over there to cause invagination. The presence of clathrin still is needed for even a regular pinocytosis that has nothing to do with receptor. This is an example of a regular pinocytosis. As you can see, there is no receptor. The picture doesn't show, but we have to have clathrin here as well. And here is receptor mediated because you can see the receptor and also you can see the clathrin. So this picture is kind of misleading because it doesn't show clathrin, but it should have clathrin as well. So let's review one more time. In the case of pinocytosis, you create inward furrows, you create invagination instead of extending out, which happened in phagocytosis. Also, remember, we can have unspecific pinocytosis that can bring anything inside, just like this one, or we can have receptor-mediated endocytosis, which is very specific. You have to have a specific ligand sitting on the receptor to come in. An example I gave you, like bringing cholesterol inside the cell, or hepatitis C that is going to affect your liver cells, or polio cells that is going to affect your neurons, HIV that is going to affect your white blood cells. Why they are very specific? Because those specific cells, they have receptor for these viruses. And this is an example of receptor-mediated endocytosis. And the only thing is left is called exocytosis. Exocytosis is when you create something inside the cell and you want to send it out. exo, outside. If this particle is too big and they cannot go through the cell membrane or through the protein in the cell membrane, we're going to put them inside a vesicle. This vesicle is going to come close to the cell membrane, is going to melt into cell membrane, and now the content is going to be out. But it's not as simple as you may think. Remember, as a general rule, nothing happens inside the cell randomly. How does this vesicle know that I have to move toward the cell membrane? I mean, imagine that the vesicle inside the cell, and vesicle can go to any direction. But how does vesicle know which direction it's supposed to go to reach the cell membrane? Also remember that just like airport, do you think that any airplane can come to any airport and sit in any gate and just ask the passenger to get off of the airplane? That is not going to happen. Each airplane should go to a specific terminal. This vesicle cannot choose any part of this cell membrane. This vesicle cannot attach to here or here or here or here. They have to attach to a specific place. But how does this vesicle know where I have to attach to? Well, the answer is we have a protein, it's called SNARE. The story of a SNARE is very complicated, is beyond the scope of this class. But all I want you to know is this. There is a protein which is called SNARE, and this SNARE is like a signal detector that is going to find another SNARE that's found in the cell membrane. They find each other, they fuse to each other, and as a result, vesicle can become part of the cell membrane and release it. The SNARE is not only for exocytosis, but we can use a SNARE for endocytosis also. Again, for our course, let's focus on the role of a SNARE on exocytosis. And that is, I hope you enjoyed this lecture. Have a good day. I'll see you in the next recording. Thanks.